Welcome, Promethea.
Hi.
Let me put your slides up here, and then the stage is yours. I can't wait to learn more about dependency injection in Bevy.
All right. So I'll be talking about dependency injection in Bevy. You may recognize that phrase because I have written a book on it, and it is fairly popular, linked around in the Bevy Discord a lot. I'm a sort of general game programmer and an amateur language developer. I'm interested in a lot of different technical topics, so I kind of bounce around. I've done graphics, I've done networking, I've done language design. I've been using Bevy since about 0.6 or so, and I'm also the developer of an old character controller crate called Bevy Mod Wanderlust, if anyone remembers that. It's defunct now, but as far as I know, it was the first character controller crate. So to get started, what is dependency injection? Because I think a lot of folks don't really recognize fully what it means. A lot of folks have heard of it from Java or C#, and usually the opinion I see is that it's kind of archaic, verbose, unnecessary, maybe performs badly, which isn't necessarily true. That can be true of implementations, but it's simpler than you think. You can see in the image, or the screenshots, it's essentially, without dependency injection, you are calling functions manually. With it, you are adding them to some framework or app, and the app calls them for you. So dependency injection just means automated function calling, where parameters are retrieved automatically and functions are called precisely when they're needed. This gives you a lot of different benefits, and the interesting part is how it's implemented, in my opinion. Usually, most languages use runtime reflection. So for example, Python, C#, Java, they all just use reflection, and usually they have an attribute system so they can read some extra data applied to different types and functions. Reflection is reading the metadata of a program at runtime. So you can read things like the syntax, the type names, the arguments that a function takes, and usually you can even take that information and start doing things dynamically that you wouldn't normally be able to. It doesn't perform very well because it's so dynamic, but it is extremely powerful. You can also technically do it at compile time in certain ways, but that's a pretty recent development, and not a lot of languages have that. It does allow metaprogramming at runtime, which is kind of unusual. In this picture, you can see something you can do in C#, for instance, where you load an assembly and then read out all of the types and their names at runtime, which is not something you could do in, say, Rust or C or C++, because they just don't have that information available. Although I think C++ specifically does have a mechanism called runtime type information. So why would you do dependency injection? What is the point? It gives you certain nice abstractions, like you can change system signatures without changing the call site. So you just refactor your system, and then it just works. The parameters will be provided automatically, and you don't have to go tie things up somewhere else, which can be really nice in a large code base where now you don't have to jump around and fix up everywhere that that function was touching. It also allows the app to manage the control flow automatically. So things like automatic parallelization or setting up data-driven execution by reading from config files become possible because the app is handling it, so you can automate it. In Bevy specifically, this is what dependency injection looks like, is right at the beginning when you're assigning systems. That is dependency injection. Specifically for this talk, I'm worried about the tuples of systems themselves, not the plugins or the schedules. Those parts are not as specific to what I'm talking about. So I talked about how usually it's implemented using reflection, and Rust does not have reflection. Yet, technically, Rust just merged a little bit of compile time reflection onto the unstable branch, but it's not really there yet. So if it's not there yet, what is Bevy doing to make this work? It isn't reflection, as I said. It's not Bevy Reflect either. Bevy Reflect is a crate developed by Bevy to implement runtime reflection. And it does so using macros. Essentially, it's just macros that read your code and generate a bunch of access functions to read information generated from the code. which is limiting because it means the macros don't have access to type information. And also, you may notice the systems themselves don't have any like proc macros attached to them. So it isn't Bevy reflect. It just Bevy reflect is not relevant to the ECS in that way. Rust's type system is the key, specifically the function traits fn, fnbut, and fn_once. The key insight is that every function or closure gets a unique type generated for it. So you can see here, if you were to define two functions, foo and bar, doesn't matter what parameters they take or return, if you get their type IDs and compare them, they will be different, and you can do that. That type implements some of the function traits. All of them will implement fn_once because every function can be called at least once. Closures might not implement fn because it needs mutable access, but a basic function should implement all three. So through that, we can get a type for every function and do some logic on it using traits. Next, we have to select a specific function implementation for a type by wrapping it in a struct, which is due to type system complications, because technically any type can have multiple trait implementations, and that means technically a function could be two functions with the same type. They probably won't be, but if a user defined a type and implemented the function traits manually, it could be, so we have to handle it. Type inference and trait inference can help deal with that later. So then we implement system for that struct and store it in the schedule to run later. And the system implementation automatically retrieves arguments from storage and passes them as arguments to its run implementation. So next I'm going to show and walk through some code from my book to illustrate this idea more clearly. So don't get too overwhelmed. I'm going to highlight specific parts at a time. This code implements system for functions with one argument. Any static type can be a system parameter, and the global storage is just a hash map of values, one of each type, instead of an ECS world, just for simplicity. So first, we define the system trait. All the system trait does is it takes in the system itself and then some resources, and it will automatically retrieve values from resources and call itself. This is what lets us dynamically call systems without caring what values they take. Next, this is the struct wrapper that we use to select a specific function implementation. So if you had implemented a type with two different functions, this is what lets us select a specific one. And this is because if we blanket implemented system for functions, it wouldn't know which one to pick by default, and then the implementation would fail. So that's what this is for. Kind of complicated type system stuff, but it is necessary. The struct manages to select a specific implementation because it is locked to a specific set of generic arguments. The input parameter is the arguments that are passed into the function. That means there can only be one matching function implementation. So then everything works. And if you only have the one function implementation, the type system will just infer it, so you don't need to specifically construct the function system. And the phantom data is needed because the input parameters are not otherwise used, so we just need to put them somewhere. Next, we implement system for the struct wrapper, which is the function that automatically retrieves data. You can see it removes from the resource cache and then downcasts and unwraps and passes it into its own function. In an ECS, this system could be more complicated. You might, for example, do some query logic here. For this example, it's just accessing a basic value from a hash map. And then finally, we define some helper into system traits to wrap the system. This lets the .add system function on app take a system directly instead of a function system. It technically isn't necessary, but it means we don't have to manually wrap every parameter in a function system when we're just trying to set up the app. Bevy's benefits from this, I think Bevy gets a lot out of dependency injection. I think it fits very well. Firstly, app definition becomes declarative. You don't have to manually set up a run loop and call all of the systems in your app in a row. You just can outline, I want this to happen, then this to happen, then this to happen, and then it will happen in the order you declared. It also lets you, like I earlier mentioned, refactor by just changing a system, and you don't have to worry about the parameters getting passed around somewhere else. The app will take care of it. It also allows you to do really cool things like hook into system sets that were defined elsewhere by using system labels and before and after, and just hooking into third-party crates or Bevy's own systems and adding logic where there was none. But there are also some drawbacks. One of them, the compile time hit, I outlined in the latest chapter of my book. I found that there was some overhead and compile time using this trick. If you were a library designer and you're thinking about using this for a library you're developing, I would ask that you consider if it will really help benefit because of this specific issue, the compile time hit. It can be pretty severe, from what I can tell. And also, it's not strictly necessary that you use dependency injection. You could just ask users to call their systems themselves. And depending on your project, the benefits might not be that much. It is also very complex for new users. Often we would see new Bevy developers join the Discord and ask, like, how does this work? It literally looks like magic. What are you doing? And a lot of times folks would ask, like, is this based on Bevy Reflect? Is Bevy Reflect doing some magic behind the scenes? They just wouldn't have a mental model of what's going on, which just makes it very confusing and feel weird to use Bevy. So that's why I wrote my book in the first place, was I understood how it worked and I wanted to help others understand how it worked. And now I'm giving this talk for the same reason. It's also pretty complex to develop and maintain. I mean, you saw the code. It's kind of a lot of hoops to jump through for I want in a loop for me. Bevy gets good mileage out of it and has enough contributors that this is worth it. But if you are a solo dev or a small team trying to work on something, that's a lot of effort to put on for something that is not strictly necessary. So again, just consider, is it really worth it? Are you actually going to benefit enough to be worth implementing something so complex? So with that, does anyone have any questions for me?
Yes, thank you so much, Promethia. I'm super excited about this topic myself. This is one of those black magic parts of Bevy. So it's always appreciated, people like making this more digestible and understandable. This was really insightful. Yeah, we have a bunch of questions. Let's actually go through some of them. What would a next generation dependency injection look like in Bevy? Are there potential improvements that would be V2 level changes?
I don't think so. I did have some ideas for how to mitigate the compile time hit without changing the API significantly, which would be adding a macro and having the macro generate code that is much less compile time overhead. So essentially, that would just be adding a system macro on your systems. And I figured out a way that you could still have systems without the macro. It would just help compile time to put system on things. Other than that, I haven't thought of any ways to make dependency injection significantly better. I feel like it's kind of already at a local maxima of like, it's very slick and clean and it just works. And I guess the other thing would be better errors, but Rust did add those better lints that the Bevy developers can customize. So the errors already got a bit better, but we'll see.
Is the system macro that you talked about, is that something that's going to be upstreamed at some point?
Maybe I'd have to go back to it and refine it. Currently, it's just an idea, and I'm somewhat short on time to work on something complicated like that, but I'm interested in seeing where it goes.
Yeah. Okay, that's super cool. Wait, where was the next question? Is there anything in progress in Rust itself to improve the compile time impact?
Nothing super specific, except that variadic generics is a feature that could lead to an improvement, because currently internally Bevy uses macros to generate implementations for systems with no parameters, systems with 1 parameter, system with 2 parameters, and so on, up to like 8 or 16. That causes a lot of compile time impact. Variadic generics would let us just define a trait once for systems with any number of parameters that could maybe help compile times. Not clear yet. It could also make it worse depending on implementation. I would like to see it make things better. I think it would not be worth using if it made things worse, but
Yes.
hard to tell. It's not implemented. I'm very excited to see when variadic generics get merged.
Okay, so there's not even like a feature flagged nightly implementation or whatever.
I don't believe so. Maybe I just missed it, but.
All right. So the next question is, you pretty much answered already, because it's about the impact on compile times. But maybe there's like a short summary. Like, is there any way to measure this that you can talk about here without having to read the last chapter of your book?
So essentially, what I did for the last chapter of my book is I generated just a simple file that was a ton of functions and adds them to an app and sees how long that takes to compile, versus what if I just called all of the functions in a row manually and see how long that takes to compile. And through that, I found that just calling all the functions in a row, pretty much instant, adding them all to the app takes a long time. That was the key insight of like, there is overhead here. I don't think it's as exaggerated as in my example, because it's specifically making it as bad as possible to see if there's anything there. Harder to measure on an actual application, for example. Like, it'd be hard to look at your actual compile times and be like, oh, 5% of this is Bevy overhead for dependency injection. Like, that's harder to measure.
Yeah. Fair enough. I mean, the second part of this question is also talking about generated code size. I don't know if that's really something that it's equally hard to probably compare, right?
Here, actually, so in terms of macro output, there's not a lot, because you're not putting it on every system. It's just inside Bevy, they generate a couple implementations. So that part isn't too bad. In terms of like generic monomorphization, so the actual final every system's generated code that goes into the binary, that I found does look like a good place where there might be a lot of overhead coming in. The system itself probably isn't changing much, because it's still just a normal function, and a good amount of it is dynamic. But specifically, I think there were a couple functions that get called in the add system call path that were generating a lot of hits in LLVM lines. I forget exactly what they were. I think one was related to debug printing. So I'd measured that. I'm not sure if it's actually relevant to compile times, but it did seem a little concerning.
Okay, I see. I'm not sure if you touched on it. I mean, in general, you said it's maybe not the right tool for everything, but the next question is about, can Bevy's DI be used in regular Rust applications?
As in terms of using the technique, yes, you could apply the same technique. For example, Axum does use the same technique that I'm aware of. Bevy specifically, the implementation is kind of built into the ECS itself, I think. Or I think it's split between the ECS and the app crates, technically. I have a hard time seeing you use those without essentially using Bevy itself, because that kind of is the core identity of Bevy. So I don't know if the implementation is very reusable without basically using Bevy itself.
But I guess there is cases where people are using those things for let's say, game or interactive use cases. At least I remember some like static site generation, I think was prototype using it. But yeah, it's not like wildly common, right?
You can definitely use Bevy itself for non-game or non-interactive applications. For example, I believe Foresight Mining Corporation or Foresight Labs, I'm fairly certain they use it a lot for things that you wouldn't call a game.
Yeah. No, I mean, I was really thinking more of the really wild use case, like the static site generation, which is not even like interact or not.
Yeah, I hadn't heard of that. That is really out there. I did once try to experiment with using it to build a compiler. I didn't like it very much, but it was interesting.
Actually, one question that since you pointed out where it's sort of the core of the Bevy engine itself, did you also familiarize yourself with other dependency injection implementations in Rust that you can compare this against?
The only one I'm really familiar with is Axum, and I haven't used Axum or looked into it in depth.
It's using a similar approach, right? Axum,
yeah, I believe so. Yeah. Same idea of using traits to detect function implementations and automatically wrap them and such.
Yeah. All right. Let's do one more before we maybe delay the rest for the end. How does the black magic of parallelizing non-overlapping systems work under the hood?
Okay, so that is a fair bit more complicated, in my opinion. But the basics are Bevy can look at a system's parameters and create basically a checklist of every resource, including entities, that system accesses, and then it can just diff that against other systems very quickly using a bit set and go, okay, so this system and this system do not conflict, therefore they can run at the same time, and it will just hand them to the scheduler to run at the same time. If they conflict, it has to generate a boundary between them so that they run serial, and then it hands that off to the scheduler and says these have to run one after the other. Very, very high level overview of how it works, but that's the basics.
And where do commands get triggered in this chain of events?
That changed enough times that I don't even fully remember. Currently, there is a system label called apply deferred, if I remember correctly, and it is also automatically inserted. I think it was between systems where one system uses commands and the next system requires anything that system was asking for. At this point, I don't know if it maybe is finally settled on just apply commands immediately.
But it would be a barrier as well where no other system can run at the same time, right?
Yes, every time you apply systems, the entire world has to sync down to one system running to apply commands.
Yeah. All right. Cool. Well, thanks again, Promethea, and everyone in chat. Please give a big hand for this super interesting presentation. And let's reserve some more time at the end for some of the remaining questions and maybe more that come up in the meantime.